Yeah, sure.
Well, you tell me. If you'd rather start with somewhere else on these 2 pages, I can do it. But if you're not sure where to start,
It's okay. I'm really bad at probability questions.
well, it's not my greatest subject either. But the basic ones I'm all right at. Okay. If you toss 3 coins, let's talk about that one.
Do you know how to do?
Sorry?
Okay. Oh, no, nothing. I forgot.
Okay. I'm not sure if I'm having problems with the audio or what, but can you hear me okay?
Yeah, can you hear me?
Uh-huh. Okay.
Okay.
Toss 3 coins. Let's list the possible outcomes. I could have heads, 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 right?
Yeah.
Now let's find a methodology that works so I don't miss anything. I could have 2 heads and a tail.
Uh-huh.
That covers all of the possibilities where the first 2 coins are on heads, right? So I could also have a heads on the first coin, a tail on the second coin, and a tail on the third coin. And I could also have a heads, a tail on the second coin, and a heads on the third coin. So those are all the 4 possibilities of the first coin having a heads on it. Now let's talk about the first coin having a tails. Well, we could have all 3 coins have tails. Now I'm going to use a very similar pattern to count through these. In other words, I've also got the choice where the first 2 coins have tails, the third one is heads, and then I've got tails, heads, tails, and then I got tails, heads, heads. That's it. There's no other combination. And notice how many combinations I have, 8. Well, that's because the odds of being heads or tails are 50-50, and if I take 2 cubed, I get 8. But this is what I would call the counting method. Okay. In terms of drawing the sample space, I'm not sure what they're asking for there. Are they asking for like a tree? In other words, some ways you might see this or like this. You could have heads, heads. You could have heads, heads.
Yeah, they're looking for like
tails. You could have heads, tails, tails, and you could have heads, tails, heads. And then you could do the same thing with the tails. Okay? So I don't know what they're looking for, but in terms of listing all of the outcomes, here they are on the left here. And the odds of each outcome are actually equal. They're all 1 out of 8. And so if you add up all of the possible outcomes, you got 8 times 1 over 8, 100%. So 100% of the times, your 3 coins will be one of these 8 sequences. And let's just make sure you know exactly what I'm talking about. In other words, we have 3 coins that are either on heads or tails. There's 1 coin, 2 coins, 3 coins. And you will not be able to find a sequence that is not one of these 8. It's either heads, 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 tails, 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 or anything else that I've written there. Okay?
Okay.
Let's go on. Just let's not get hung up on this problem. There's a lot of problems to do here. Hold on a minute. Can you see that okay, or do you have the page in front of you? I can see it fine.
I have the page in front
of you. You can probably see it, but I don't know if you can read it off my screen or
I have a page right in front of me.
not. Okay, good. Because I don't know how to expand this. I don't know how to zoom in on this. What's the probability that the spinner stops on an even number? How many numbers are there in that spinner? How many? Count them.
Can you hear me? 10.
Okay. So there's 10 possible outcomes, and they're each equally likely because the angle is the same. The central angle is the same on each of those sections. So there are 10 possible numbers. Now, how many of those 10 numbers are even numbers?
6.
That's what probability is it's always the number of successful outcomes, which in this case is even numbers, over the total number of possible outcomes.
Okay.
So that's where we get 6 out of 10. Now, if you spin the thing 20 times and it only lands on an even number 8 times, well, now you're talking experimental probability. In other words, there's two kinds of probability. There's theoretical and there's experimental. Theoretical is what you can calculate. That's what we calculated. It was 3/5. Okay, and that's based on the fact that each angle is the same, and that when you spin this thing, it has an equal likelihood of landing on any of the 10 numbers. Well, when we spun it 20 times, we only got 8 even numbers, which is 2/5, not 3/5. So what's going on? So anyway, the answer to B is 2/5. C, are the probabilities the same or different?
Different.
Why? Why is the theoretical probability different than the experimental one?
Because theoretical is what you think is going to happen.
The answer is that the experimental was not based on enough spins. That's why they're different. We based it on 20 spins only. Well, think about spinning just once. Came up with an odd number, you'd have 0 success, right? So for the experimental probability to get close to the theoretical probability, you need a large sample size. And 20 is nowhere near large enough. If we spend it 20,000, well, then we're going to get closer to 3/5. We'd have close to 12,000 even numbers. Okay, that's equal to 3/5. But you can't tell much of anything by just doing 20 times. It's just not a big enough sample size. And that is the explanation to why they're different.
Right.
If you had a large enough sample size, guess what? They wouldn't be different. They would be the same, or very, very close. Okay? Now, number D, are the spins independent or dependent? And what they mean is, are they independent? Is one spin independent of the next one? Or is it dependent? Are the odds of it landing on an even number, do they change from spin to spin?
Yeah.
No, they don't. The theoretical odds are 3/5. That's what they always are. I don't care if you spun this thing 100 times and came up with 100 odd numbers in a row. The odds of the next spin being an even number would be 3/5. In other words, the theoretical probability rules. But what happens is the experimental probability doesn't always agree with the theoretical. Let's take a roulette wheel in Vegas. Okay? Pretty easy to calculate the experimental or the theoretical probabilities. There's 38 numbers. The odds of it landing on any given number are 1 out of 38. Now let's say that the casino starts losing money to a roulette player, and they discover that this player is betting 3 or 4 numbers more than anything else, over and over and over and over, and he keeps winning money. Well, what's the answer to that mystery? The answer is you got a bad roulette wheel.
Okay.
Okay? And that's how they tell those kind of things. There are bad roulette wheels. I know people who have made money off of playing roulette. And they don't do it because you're supposed to be able to do it. They've done it because they scouted all the roulette wheels in the land and they found a few that didn't appear to be random, that didn't appear to give equal likelihood to every number. Some numbers the ball was more likely to land in than others. Well, that's bad for the casino because you've got a wheel that is not random.
Yeah.
Good for the player trying to beat money, take money from the casino, but the casino, of course, depends on everything being perfectly theoretical. So all of their roulette wheels have to be perfectly balanced. The guy who puts the ball into the roulette wheel can't put it in too fast, can't put it in too slow. He does it the same way every single time. In other words, he's trying to do it in a way that nobody can predict where it's going to come up. Because if anybody can predict it, they can bet and make money on it. So this question of theoretical probabilities versus experimental probabilities is actually a very, very interesting question when it comes to actual life. There was a situation, let me explain this to you because this is really useful. And I don't know if you know how to play blackjack, but it doesn't really matter. The odds on blackjack, the theoretical odds are the house is supposed to win 2% of the money wagered. Okay? With me?
Yeah.
Well, they measured their win rate in South Africa at all their casinos, and they weren't winning at 2%. They were winning at like 1%. And so they correctly jumped to the conclusion that somebody was cheating them because the theoretical probability was not matching what they were actually doing. And they came to the conclusion that somebody had to be marking the cards. And they went back to the factory cards and they examined them. Guess what? They discovered markings on them. And they figured out who had been cheating them, and they caught them. And the only way they were able to do it was because the experimental probability did not match the theoretical probability. And the one thing that the laws of probability say are that they have to match. As long as the sample size is large enough, the experimental probability will always go to the theoretical probability. Won't maybe equal it exactly, but the greater the sample size, the closer it will get. In other words, maybe it's 12,010 instead of 12,000. So that's not exactly equal to 3/5, but it's very close.
Yeah.
If I increase this to 200,000 instead of 20,000, it'll be even a closer percentage-wise to it. And there's actually a theorem in probability that's called the law of large numbers, which says is that as your number of samples approaches infinity, the experimental probability will approach the theoretical probability. Very important concept in the world.
Mm-hmm.
All right. Let's go on. Shall we go to 3?
Yeah.
Okay. If you want to skip around, in other words, we only have another 40 minutes, so I'm not sure we're going to get to everything on both pages. So if you want me to skip, say so.
Okay.
Otherwise, I'll just go 1, 2, 3, and so forth. And we'll go as far as we can get.
Okay.
All right.
I'm just bad at the probability ones
Okay.
question.
Okay. So 4.
So like this whole page would be good to like review over.
All right. Let's look at 4. First of all, if you have the probability of A equals 0.3,
Mm-hmm.
and let's assume that I knew what the probability of B was. Let's say it's equal to 0.2.
Mm-hmm.
Then if I want the probability of A and B,
Mm-hmm.
I just multiply those two numbers together. It's the probability of A times the probability of B. Or, in this case, 0.06. In other words, if both things have to happen, the probability of both of them happening is going to be 0.06. When you're
Mm-hmm.
dealing with ands, you multiply. If you're dealing
Mm-hmm.
with ors, you divide. Okay, now let's go back and look at this. Because all they gave us was an algebra problem here. So
Mm-hmm.
probability of A is 0.3. They didn't give us the probability of B. That's what they want us to solve for.
Mm-hmm.
What they gave us was the probability of A and B being 0.08. Well, if we know the probability of A and B is the probability of A times the probability of B, then like I said, we have an algebra problem. That's 0.08. Probability of A is 0.3. Solve for the probability of B.
Um, 0.267.
Well, it's 0.08 divided by 0.3, right?
Yeah.
And that gave you 0.267?
Uh-huh.
Hold on. I'll do it in my calculator. For some reason, that doesn't sound right to me. Nope, that's right. So that's the answer.
Okay.
In other words, this is the key equation to know right there for these kind of problems they're giving us.
Uh-huh.
And this is only true if the events are independent of one another. If they are dependent on one another, then we have a different equation that we use. Okay? So the probability of A and B is only equal to the probability of A times the probability of B if they're completely independent. Let's say that I'm flipping a coin and I want to know what's the probability I'm going to get a heads on the first flip and a tails on the second flip. Well, those two things are independent of one another. The odds on the second flip have nothing to do with the results of the first flip.
Mm-hmm.
So whenever they're independent, use this formula. Okay.
Okay.
Let's look at the next one, 5. Here they give us the probability of A is 0.5, and here they do
Mhm.
give us the probability of B, which is
Mhm.
0.35. So what is the probability of A and B?
It'd be A times B.
0.5 times 0.35.
That's 0.175.
That's the answer.
Mhm.
Okay? All right. Let's go on. The equation is slightly different if they're dependent, but let's not get there yet. Let's go through some of these others.
Okay.
We'll eventually find a question where there's a dependency, and then we have to use a different formula. Okay, a die. Are you familiar with dies? Dice?
Yes.
Cubes. There's 6 sides. The numbers
Right.
1 through 6 are on each side of the cube. Okay? So what's the probability
Okay.
with one die that you'll roll a 3?
1/6.
Correct, because there's only one side that has a 3 on it. And there's 6 possible sides that it can come up. What's the probability you'll roll a prime? Well, first of all, let's list the 6 numbers that are on the die. Tell me which of these are prime.
1, 3, and 5.
2, 3, and 5.
Oh.
One is not prime just because the definition of prime is it's a number that can only be divided by 1 and itself.
Okay.
So 2 fits because 2 can only be divided by 1 or 2.
Mhm.
3 fits. 4 doesn't because 4 can be divided by 4, 4 can be divided by 1, but 4 can also be divided by 2. So it's not prime. So what are the odds that I would roll a prime number when I roll a die?
3 out of 6.
Correct, which is 50%. You always want to reduce those to 1/2, which is equal to 0.5, which is equal to 50%.
Uh-huh.
Okay? I don't know how
Okay.
your teacher wants the answers. She may accept 1/2.
She does either.
Okay, 1/2 would certainly be an acceptable answer. There's a
Mhm.
1 chance out of 2 that you'll roll a prime number. What's the odds you'll roll a number greater than 6?
0.
Correct, because there are no numbers greater than 6 to roll. You roll a factor, is that supposed to say of 4?
Yeah. Or 4 or
Or
an
an
even.
even number? Well, let's look and see which numbers qualify. Factors of 4. Well, let's circle all of those. Those are the factors of 4, right?
Uh-huh.
4 times 1 or 2 times 2.
And then it says or an even number 2.
Okay, so now I'm going to circle that one. So now add up all of the successes. Remember, it's the number of successes divided by the number of possibilities.
Mhm.
So what is this one?
Well, it's an or probability. So wouldn't it be 3/6 plus 3/6?
Well, it's easier than that to do. Even though it says or means, what's the probability that I'll roll a 1 or a 2 or a 4 or a 6? How many possible successes are there?
4 out of 6?
Out of 6. So 2/3. Like I said, you never want to give that as an answer because it's not simplified.
Uh-huh.
So you might come up with that, but then simplify it always. So this is the proper answer.
Okay.
Okay? All right, let's look at 7. You roll a die 8 times in a row. What is the probability all 8 rolls were even numbers? It's the probability that your first roll is an even number.
3 out of 6.
Okay, that's 1/2. So the probability your first number is an even number is 1/2. What's the probability your second number is an even number?
1/2.
And if it has to occur, then I'm multiplying all of these. So what I really have is 1/2 to the 8th power. Well, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th is 128, 2 to the 8th is 512. So it's 1/512. There's the probability that I would actually roll an even number 8 times in a row. And it's always multiplying if both of them have to occur. If, you still there, Emma? Yeah, it looks like you got kicked out of my meeting.
Yeah, I'm not sure. I'm going back in. Hold on.
Okay, I won't change the meeting ID number. Go ahead and use the same meeting ID number. Are you on your iPad?
Yeah.
Okay. Let's just pay attention to that and see if we can figure out what's causing you to get kicked out. Okay?
Okay.
It looks like you're back in now, so I'll hang the phone up.
Okay.
Can you hear me? Unmute your microphone again. In the upper left, you gotta unmute it. I cannot hear you. I suspect you can hear me, but I can't hear you. Your microphone, are you there now? I will call you again on the phone. Emma? Emma? Here, hold on. Let me put it on speaker. Sorry.
Okay, I'm sorry. I don't know what's happening.
It looks like you're in the meeting. You can see my screen, right?
Yeah.
We just didn't have audio. Look up above with the audio tab where it shows a picture of a microphone. Is there a line across that?
No, it's green.
Ah.
Can you hear me now?
No, but something just happened.
It's okay.
Because I heard, that's okay though. As long as you can see my screen, we can use my phone for the audio. In other words, we don't need to use the audio from GoToMeeting. It's just usually a little bit better audio. The audio from my phone is not that great, but since we can't figure out exactly what's going on, we'll use the audio from my phone.
Okay.
All right, as long as you can see my screen. I just wrote a number on my screen. What did I write?
7.
Yeah, okay, cool. All right, so back to that problem. It's 1/2 times 1/2 times 1/2 times 1/2 8 times. Because the probability of rolling an even number is 1/2 on any given roll. And there's no dependency. The odds of rolling an even number on the second roll are exactly the theoretical odds 1/2, 3 out of 6. So to actually do it 8 times in a row, you got to multiply 1/2 times 1/2 out 8 times, which is 1/2 to the 8th power, which is 1 over 512. Is 512 correct? I'm not sure that that's, now that I think about it. 2 to the 5th is 32, so 64 would be to the 6th, 128 would be to the 7th. No, that's 256. 1/2 to the 8th is 1 over 256. I did it wrong when I was doing it in my head.
That's okay.
Not that they would really expect you to know that without a calculator. So you would normally put that into the calculator and either answer with a decimal, or this is actually the preferable answer. To me, I'd rather see 1 out of 256 than some tiny decimal that looks like 0.04 or something. You know what I mean?
Okay.
All right. So let's look at number 8. You choose 3 cards from a deck. You keep each card. What's the probability of choosing 3 face cards? Well, the very first card you picked, how many face cards are in a deck? 52 cards in a deck of cards. Assuming they're counting 10s, jacks, queens, and kings as face cards, then there are 16 face cards out of 52. Now, I'm not going to simplify that yet. There's a very good reason why I'm not. That's the probability that your first card is a face card. Well, they need all 3 of them to be face cards, right? So the first one's got to be a face card and the second one's got to be a face card. Well, if the first one is a face card, what are the odds that the second one's going to be a face card? How many face cards are left in the deck?
15
out of 51, because there's only 51 cards left in the deck.
Okay.
Times 14 out of 50. In other words, the odds of getting a third face card require that you had to have gotten a face card on the first draw and a face card on the second draw. So the odds of getting a face card on the third draw are 14 out of 50.
Okay.
And now you use a calculator to come up with that number. 16 times 15 times 14 divided by 52 times 51 times 50. I don't care what the number is. You shouldn't either at this point. What you're trying to learn is how you arrive at that number, not what the number is. Your teacher doesn't even care what that number is. If you put this down, you probably get full credit for the answer. As opposed to if you put a number down, let's say you just put this down. I don't think she'd give you full credit, even if that's correct.
Yeah.
She wants to know how you came up with it. Well, how you came up with it was by figuring the odds of the first card being a face card, multiplying it by the odds of the second card being a face card, multiplied by the odds of a third card being a face card. And they're not the same for each one. Each one of them is not 16 over 52, because the nature of the problem is they have to all be face cards. So this has to have happened, which means the odds of the second card are 15 over 51. That has to also happen, which means the odds of the third one are 14 over 50. These would be dependent events.
Okay.
If you said, what are the odds of getting a face card if you draw one card from the deck? Well, it's 16 over 52. Now let's put that card back in, shuffle the deck, and say, well, what's the odds of getting a second face card if you now draw again? Well, that's also 16 over 52, because now there's 52 cards back in the deck again. And now you take that face card and you shuffle it back in and draw a third time. Well, now it's 16 over 52, and the odds of getting 3 straight face cards is that number. Different than the first case.
Yeah.
The difference is the second case is with replacement. This problem that they gave us is by definition without replacement, because they're dealing you 3 cards from the deck, not one at a time. They don't deal you a card, you look at it, oh goody, it's a face card, and then you give it back to them, they shuffle it up and give you another one. That's not the way this one works. This one works where they give you 3 cards from the deck. Now you got to figure out what are the odds of all 3 of those being face cards. Now we're using this top method here, not the bottom method. The difference in those 2 answers depends on whether or not you're replacing the card each time.
Okay.
Okay? All right. What's the odds of choosing the jack of diamonds? Just that alone. What's the probability of choosing the jack of diamonds? How many jack of diamonds are there in a deck? There's 1 out of 52 cards. Now, it wants to know the odds of you choosing the jack of diamonds and then another diamond. Well, how many diamonds left are there?
12.
And how many cards left are there?
51.
So whatever that product is. And that's presuming you get both cards at the same time. If you take the jack of diamonds, in other words, if you're lucky enough that you choose the jack of diamonds, and then you give it back to them and they shuffle it back in, well, now the odds of getting another diamond are 13 out of 52. But if they gave you both cards at the same time, well, then the first one has to have been the jack of diamonds, and now there's only 51 cards left, and there's only 12 diamonds. So this is another problem where these are dependent. This is called without replacement. They usually categorize these problems with decks of cards as with replacement or without replacement. And depending on which you choose matters.
Okay.
Okay, let's go to the next page.
It says at the top, since you can't read it,
Okay.
it says, get the percent of the curve under the normal
All right.
distribution.
Believe it or not, I understood that. Here, I'm going to draw this slightly differently.
Okay.
Here's a normal distribution curve.
Okay.
And that is the mean. Okay? Now,
Okay.
when you have a bunch of data, you usually have the mean and you have the sigma, which is standard deviations. Okay? Well, if I go out 1 standard deviation, then that point there is x, the mean, plus 1 standard deviation. If I go there, that point is the mean minus 1 standard deviation. You with me?
Yeah.
The rules of normal distributions say that within 1 standard deviation, 68% of the data will lie. Hold on, I didn't quite draw that correctly. That's my point right there. Let me draw it in, I'll draw it in black just for illustrations. So in this yellow area there, 68% of the total area under that curve is going to come in that yellow area.
Okay.
Okay? Since it is symmetrical, then 34% is in the left part of that, and 34% is in the right part of that.
Okay.
Okay? Now let's go out 2 standard deviations. So this point is now x mean minus 2 sigma, and this point is the mean plus 2 sigma. And this time I'm going to use a different color, red, to draw my dotted lines. So if I want what percent of the total area under that curve is the red, well, 2 standard deviations gives you 95% of the total area is in the red.
Okay.
Okay. Well, if I finish graphing this, in other words, if 95% is between my 2 red lines, well, this has to be 47.5%. And since that's 34, this has to be 13.5. That block right there is 13.5% of the area under the curve. So is this. That's 13.5. And they only take you out 3 standard deviations. Okay, this point being x, the median, minus 3 standard deviations. This point being the median plus 3 standard deviations. This one I'll draw in green. And now I can say that the total area in the green part is 99.7% of the area under the curve. Well, if I go back and figure that out, half of 99.7 is 49.85. So from my left green line to my median's got a total 49.85. Well, I've already got 47.5. So by subtracting the 2, it gives me 2.35 is in that block of the area under that curve, and another 2.35% over there. Now, if I were to add up 2.35 plus 13.5 plus 34 plus 34 plus that, I get this number. 99.7% of the data is found within 3 standard deviations of the mean. All right, now we're ready to answer these questions. How much of the data is to the left of this red line? Let me back up one more thing, because there's something else you have to know. The area under the curve completely to the left of the mean is 50%.
Yeah.
So what do I total? I'm totaling 49.85%. Well, the rest of it's got to be 0.15%. So now you're ready to answer this question. They're going from one standard deviation all the way left. So I'm adding up 13.5% plus 2.35% plus 0.15%.
Is it 15.85?
I get 16.
Okay.
And 16's got to be right if you think about it. In other words, if 68% of the curve lies there, then 32% of the curve lies everywhere else. Half of it is 16%. So if I want the total area of the curve from that point all the way over, it's got to be 16%. And I do it knowing that to the left is 50%.
Yeah.
All of the area under the curve to the left of the mean is 50%, and all the area under the curve to the right under the mean is 50%. And this problem is indicating everything to the left of the mean minus 1 sigma, which in our case is that point right there. So they want all of the area to the left. The curve you really want, the thing you really want to memorize here is those numbers in the blocks that I've drawn. This one is on the right side. It's another 0.15. In other words, it's symmetrical. Okay? So know that if you're looking for that area only, it's 34%. If you're looking for this area only, it's 68%. In other words, you just add up all the numbers you're looking at.
Okay.
Okay? Let's look at this one, the middle one here. That says the mean plus 2 sigma, correct?
Looks like it.
Okay, well what they're referring to, I'll shade it in orange, is all of that area.
Okay.
Okay? Well, to get all of that area, add up everything else, subtract it from 100%, and you get the rest of that area, or don't really need to do it the hard way, just add the two that we see. We can tell that 2.35% plus 0.15% is going to be our answer. In other words, this 0.15% is the rest of it. 2.35% is between 1 and 2 sigmas to the right of the mean. But all of the area is this area. I hate it when I think I'm on right and I'm actually on erase. All right. So all you have to do is figure out where the point they're talking about is, and it says the mean plus 2 sigma. Well, that's this black line right here. That's my mean plus 2 sigma. So I just need to add up those panels to the right, and that comes to 2.5%. Now, the bottom one. There's only 2 panels they're talking about. And that's this panel here and this panel here. You see how I get that? How I know that that's what their graph is asking for. Because their graph, that area is between the mean minus 1 sigma and the mean minus 2 sigmas. Well, there's my mean minus 1 sigma. There's my mean minus 2 sigmas. So that's how I get that green area. And then they also want the other side of it. In other words, between the mean plus 1 sigma, which is this point, and the mean plus 2 sigmas, which is that point, which gives me this green area. So the first thing you need to do is figure out which panels they're referring to when they give you these graphs. In other words, you always want to be able to create from scratch this drawing,
Okay.
where there's basically 1, 2, 3, 4, 5, 6, 7, 8 panels. 8 panels covers the complete area under the curve. And as long as you know what percentage of the area is in each panel, then it's really just a question of adding them up when they give you a problem like this.
Okay.
Okay? So no matter what combination of panels they give you, let's say they want the area under the curves that are this panel, and this panel, and that panel. Well,
Okay.
it's not a normal looking problem, but it's certainly easy. It's 2.35% plus 34% plus another 2.35%.
Yeah.
That's how you do them. The key is
Okay.
knowing how you get these panels, and the key on that is knowing that 1 sigma is 68%, 2 sigma is 95%, 3 sigma is 99.7%. And that allows you to figure out each of these numbers that goes in each of these panels. In other words, I'm not really suggesting you memorize each of these numbers. What I am suggesting you memorize is the following. This is the only thing you have to memorize. 1 sigma, 68%. 2 sigmas, 95%. And 3 sigmas is 99.7. If you know these 3 numbers, then you can create all the numbers that belong in these panels. Notice that the 34% is half of 68. So that's, if you know these 3 numbers here, then you can create these 8 numbers here. And that's the way I would do it. I don't have these memorized. I would never memorize these. But the 3 that I do have memorized are these 3. And knowing these 3 allows you to draw this curve the way I have and label each panel as to what percent area under the curve it is.
Okay.
Okay, Emma, I have a 5:30 unfortunately that I got to run to. And maybe next time we'll figure out what happened with your audio.
Yeah. Also, I have spring break next week, so I won't have any.
Okay, I will cancel your next week's session, and I'll talk to you 2 weeks from now.
Okay. Sounds
All right.
good. Thank you.
Okay, Emma. Bye-bye.